So our next speaker is Dr. Lalithambika. She has led our Gaganayan mission for ISRO, and so we can call her the woman in charge of our rocket program in the recent past. She has a BTech and MTech from Engineering College in Trivandrum, and she's been at the Saravai Center for Space Research, I think since the late 80s, and the stage is hers.
Thank you so much for that kind introduction. It's a great pleasure to be back here at IISc, and I got the opportunity to listen to the morning session as well, most interesting, and this is coming immediately after Professor Vijayaraghavan's talk and Dr. Ramdas' talk. And Professor Vijayaraghavan has been guiding us through the Gaganyaan program, and Dr. Ramdas and NIOT has been with us. They are our partners. So it's most fitting that it's coming here. I have only a very few slides. I think we are on the last slide, long slide actually. Okay, so in keeping with the theme of the symposium, I'll be talking about extreme habitats in space. This is from the human point of view, not from microbial environments. I'm looking only from human habitation point of view. So in my mind, there are three aspects to it. One is when the human is within the cabin, whatever be the kind of mission. The next is when he is outside in space, and the third would be when he or she is on a different planetary surface or a heavenly body. So it's arranged in that manner. So first I am just giving a mission profile. Of course this is a low Earth orbit mission profile, but it can be stretched to an interplanetary mission as well. So what we initially have the liftoff from the surface, and at that time the humans are inside, safely inside the capsule, and as you ascend, if anything goes wrong, if there is any anomaly, then you have the screw escape system which will come into play and bring them back safely. Otherwise they will be going all the way up to orbit if that is the mission. So the most useful, the most common mission nowadays is the low Earth orbit. So then they may be spending, depending on the duration of the mission, they may be spending up to a week in low Earth orbit, or they may be spending up to a year. That I think that's the current record in the International Space Station so far. And if the mission calls for exploration of the moon or Mars at a later date, then either you will be going from the low Earth orbit or you will be going straight, depending on the capability of your launch vehicle to deliver the required delta V. And whatever be the mission, then you must have the other phase as well, where you will be coming back to Earth. So you will be firing some deboost motors, and then you will be reducing the velocity, and then you come into the atmosphere and you must land safely. So either it could be on land or it could be in the ocean. In either case it has to be a soft landing. So you will have a region where the parachutes open up, could be around 7 to 10 kilometers. You may also have a retro motor if it's a land landing. So I will use this to just explain the challenges as well. Okay, so I have given the environmental challenges here. Again I will go from liftoff. Because we are having the humans and all the associated paraphernalia, including the environmental control and life support systems and the further propulsion system, this will be a very heavy module. And in order to take that heavy module from the surface of Earth to wherever you want to go, you need to have a very heavy launch vehicle as well. Normally there will be solid boosters. So these will be associated with very high vibration levels and very high acoustic levels at the liftoff. So what is usually done is you will be having on the ground also, you have to protect the launch pad as well. So there will be water will be pumped in so that the acoustic noise is reduced, and there will be flame deflectors as well. You might have read that the Starship's first attempt, it practically destroyed the launch pad because they decided not to have this water pumping. Of course, I think they will introduce it, otherwise the problem is, it will be there. And so this will be felt by the crew who is sitting inside. And in order to develop the required velocity, you necessarily have to have high acceleration levels, at least in the lower stages. And the human body is having a different sensitivity to acceleration about the different axes. So it can tolerate the acceleration best through the chest, and the tolerance is least in this direction. So the seat will be, in fact I have put all the mitigation in this box here. So I'll deal with the mitigation as we go along. So in order to reduce the high acceleration levels to within the limits which are tolerable by the humans, which will be most significant in case of an abort, the trajectory itself will be shaped. So you lose out on the performance in the process. So if a launch vehicle is originally capable of taking say 10 tons to low Earth orbit, with this trajectory shaping and the other aspects to increase the robustness, it is called human rating. So that there is the possibility of failure is brought down to near nil. That will reduce the performance to, from 10 ton, it may be able to take only 7 ton to low Earth orbit. Of that order, there will be a reduction. And the seat position is usually, you would have seen that they will be almost lying down. That is to take the acceleration about the axis where you can tolerate it. And then you have, then from here I am looking at the descent. So here what is most important is that you are re-entering the atmosphere at a very high velocity. There will be re-entry thermal environment will be very severe outside. So whoever is sitting inside, when they are looking out through the porthole, what they will be seeing will be the flames. But it will not enter because you are having a very good insulation. And this is why that Columbia disaster, we are all familiar with it. What actually damaged was during the ascent, but it created the damage and the punch through during the descent. So then the flight suit is usually worn during both ascent and descent. This is to protect in case of an inadvertent hole or some decompression if it is happening within the capsule. The humans who are inside should continue to be safe. In one of the Soyuz missions, the earlier Soyuz missions, the capsule was recovered intact, but the 3 people inside were dead because they were not wearing the suit. So this is a standard procedure now. And once you are here, of course, what is most important is everybody knows, but I'll just tell again, we are in a microgravity environment, so the gravity levels which we will be encountering will be maybe some 6 to 10 orders of magnitude less than you will be having on the surface of the Earth. And there's also low level radiation. For a short duration mission, it's generally not that much of a concern because of course there will be some shielding, but the exposure duration is small, and if you are in low Earth orbit, then you are well protected by the Earth's environment, the magnetic field which is there. And also there is the orbital debris is another threat, and this is in fact a threat even in the launch phase. But almost all the big particles which are enveloping the Earth, they are all categorized and their paths are well known. So because of that, in the launch phase, if there is a possibility that one of these might be passing your path, then we will shift the launch. Because we normally have a launch window, it could be, it will be giving a cushion for any launch hold, and in addition there will be some leeway for such delays to avoid any debris that is likely to come. But if you are already in orbit, then what we can do is to maneuver so that you are not in the path. It will be wasteful of whatever thruster you are carrying, the fuel will be spent in that, but there is no other way. Of course, for very small pieces again it will be shielding, there is nothing else you can do. But this problem is becoming more and more as the years go by, and we are having more and more debris. So probably the passive way in which we are doing now will no longer suffice. It has to be some kind of an active space situational awareness so that it can be done maybe autonomously. So now these are all from the point of view of crew safety. So for crew comfort, this part has already been touched upon in somewhat good detail by Dr. Ramdas, and there was also a question, I mean, what are the commonalities between deep sea missions and space missions? Probably you can see for yourself that there are great commonalities. You are in an isolated environment in both cases. You do need an environmental control and life support system without which you cannot sustain life. And whatever that everybody is being in an enclosed environment, that is also common to both in addition to the other challenges. But there are certain differences as well, that while the environmental control and life support system does have, it needs to maintain the cabin temperature, the relative humidity, and also the pressure and the partial pressures close to what we encounter on Earth. One difference between deep sea and space is, of course, the absence of gravity. So because of which the human body, its posture completely changes, its natural posture. So the head will come down and your hands will go up. So whatever equipment the humans have to use in space, they have to be positioned differently, otherwise it will lead to fatigue. And this will be very important for long duration missions where they have to maintain their level of alertness for long periods of time. So this ergonomic design for space, that is in fact one major area, and everything, it includes everything, including the placement, the positioning, the lighting, all come under this ergonomics. So this last part is the maintenance of the crew health. Of course, food and water are mandatory. So again, here again there is a major difference between low Earth missions and missions where you go beyond Earth. Because we have the regular resupply missions in low Earth orbit. If something is exhausted, then you push all the waste materials into something and then either you throw it out and it re-enters and burns up, or you will store it so that when the next supply vehicle comes, you take on board all the provisions and then you push it into that and then it goes back. This cannot be done on a mission where you are going beyond Earth orbit. Even in low Earth orbit, it is really not a very good way of sustaining. So there's a lot of experimentation going on with some level of success on space agriculture, then reclaiming and reusing as much as we can of the waste, especially the water, can be used for various purposes. And personal hygiene, as in deep space mission, as in the deep ocean mission, this is a major area because the design of space toilets, it's already a lot of designs are there, but there's still a lot of scope for improvement in this area. And this last one is, again it is obvious that in the conditions prevailing in orbit and in space, wherever you are, continuous health monitoring, I don't know where, continuous monitoring is required. So you need to have audio and video communication with the ground where a doctor will be sitting and will be monitoring whether they are in good health, and if there is any issue then immediate there will be some intervention so that things do not get worse. And this part also I want to talk about once they come back, especially for the Indian mission where the recovery is planned in sea, then you will be splashing down in the ocean. So you need to be aware of the ocean state at the time of splashdown. If it is very rough, then the people who are inside will also have a very rough time, and it will also be difficult for the recovery mission to take place. So short missions have to be timed so that this is also another factor that is considered. and the ships which will be in position, they have to be enabled with all the positions so that they can immediately go, and the cabin can be secured and the people brought out, and in case of a long mission they will need some rehabilitation as well, which may not be a big issue for a short mission. So that is where we are now, and that's where we have at least some level of experience, that and this, where people are going out of the capsule and they are doing some activity outside, where they are protected by spacesuit. We in India, we do not have any direct experience of this, but if you are looking at ourselves as a global community, yes, we do have a lot of experience in this. And this spacesuit, as in contrast with the flight suit which I was mentioning, this is meant for protecting against vacuum because they are outside, then radiation, and if you are in the sunlight, then it could be upward of 250 degrees Celsius. If you are in the shadow, it could be extreme low temperature, and the small particles of debris which will be floating around. So again, the extravehicular activities are also normally scheduled for periods where there is lower risk of a debris impact. Now, once we go beyond, and I would like to also comment on this particular picture, which is a very famous picture. I am sure many of you will be knowing who this is. Who is this? This is Buzz Aldrin on the moon, and Neil Armstrong is reflected here. So what I want to say here is, at that point of time, the appreciation on the effect of the space weather and the radiations which could come in case of some solar activity, that appreciation was not so high. So in case the Apollo missions had happened at a time when the solar activity was very high, then their possibility of survival itself might have been in question. So, but now we have this awareness. It is much more awareness which we have, but still it is very important to have this prediction, space weather modeling as well as prediction. A lot of work is happening there to improve, so that as we go into further missions where galactic cosmic rays also become very important. Beyond low Earth orbit, there are many other sources of radiation which become very important. So we must be able to predict, and we must be able to also protect the astronauts. So we are in fact hampered with very little data in this domain, because nobody has ever gone beyond the moon, and no one has gone on long missions also beyond a year, not even in low Earth orbits. So maintaining the physiological health and the psychological health for long periods of time, that is an area where globally a lot of work is happening. In the simulators, of course, we can get some amount of data from the simulators on Earth, but the only problem there is that at the back of the mind of the people who are participating in the experiment, they know that they are on Earth. They can come out at any time. So that it really makes a difference. And this is again, that's what I have elaborated here, that very long habitation in hypogravity environments, definitely there will be physiological deconditioning, and when they come back into a high gravity environment, then there could be issues like cardiac issues could be there. So this has to be mitigated, and this constant space radiation and the increased radiation in the event of a solar storm, that's what I was trying to tell there. And the psychological consequences, suppose you are alone, then of course there's a isolation, but suppose you are with one or two other people, then the interpersonal dynamics come into play. Of course, during the selection process itself, normally the compatibility will be assessed for a set of crew, so that such issues do not happen. And we have had instances where the communication with the ground had also broken down. So in the absence of in an artificial environment where you don't have the normal cues, like normal physiological and psychological cues, everything is altered in an enclosed artificial environment far away from the earth. So the human behavior itself can alter. So this is also another challenge that will come as we move further into deep space missions, that they need to be at the top. Maximum alertness and productivity and creativity all have to be maintained. So we have to find out ways and means of doing this. Okay, and this is my last slide. So now suppose we consider another heavenly body surface. The two possibilities as of now are only moon and then later on Mars. So the surface of the moon, we know that it does not offer any kind of protection. There is no magnetic shielding, there is no atmospheric shielding from the galactic cosmic rays or solar particle events. It is not there. Whereas on the surface of Mars, the radiation exposure will be less because you have this carbon dioxide, and carbon dioxide does bring down the radiation at the surface. But you definitely need to have further protection, and this will be offered by the regolith. So definitely it is advisable to build the sleeping quarters far below the surface, and this I am sure many of you will be knowing. This is a picture of the lava tubes. Collapsed lava tubes are there, and intact lava tubes are also there on Moon and Mars. So they would be offering a kind of habitat where the temperature variations are much less than on the surface, and in addition they will also provide some protection from the radiation. So all this would be explored in great detail as we go along. Okay, there's one more thing I wanted to tell which I forgot to tell, is that there's one more consequence of moving beyond low Earth orbit. What do you do when you want to spend a lot of time in low Earth orbit? You move from a cramped capsule to a bigger space station. So the space station volume would be like a Boeing with only some 3 or 4 people inside. It is spacious enough to carry all the exercise equipment, to do all the experimentation, and then have a lot of time, space to yourself. But when you go beyond, the current launch vehicle capabilities do not allow you the luxury of huge habitation modules. So if you are looking at the Crew Dragon or you are looking at the Orion, the volume that is inside may be 1/100th that is offered by a space station. So if you are, in fact, those modules are meant to be used for moon missions and later on for Mars missions. So there will be a cramped area where these people will be, and so the possibility of putting in large exercise equipment also will not be there. So this is something for which some kind of workaround would be required, and I think ISC is also working on flexible habitat modules. Such add-ons, if we are able to carry, then we may get some more space for other activities. So this point I had already made, that space weather modeling and prediction, they become extremely important as we progress in space, and the engineering as well as the medical countermeasures and the ergonomic design practices have to be defined and implemented before we even think about extraterrestrial colonization. Thank you so much.
Go ahead. I think you can shout it out. No worries. Yes.
So, can we plan to send robots instead of human beings? Because until unless if it's specifically for human habitat building, for other purposes we can send some robots or something which would.
should do. And even if you want to send humans, you should first send robots and then pave the way and then only hold on.
Okay.
You mentioned that these extravehicular activities are planned when there is very little space debris, right? Is there a way to determine that upfront right now?
No, actually,
You want
you
the...
can hear me.
Yeah, I mean, the other one.
No, what I want to say is that there is a cataloging of all the bigger pieces of debris. This is true only in low Earth orbit. So we know their paths. And so we know where we are. Yes. So we can plan accordingly. It's possible in low Earth orbit. But of course, beyond there is no cataloging. And beyond you are not expecting debris. It may be meteorites. That's all.
One more question maybe?
So, apart from racing to send things in space, are the space agencies thinking of like removing the space debris which will live in the space?
Yes. Yes.
Are there any design
There are
models?
startups also who are planning to do that. You attach some aerodynamic desalator onto the debris, and then with the drag, it will slowly come down and burn itself up. That is one way. And if you are having some defunct satellite, which could be brought back to life, suppose it's only fuel that is exhausted. So this refueling is being explored. There are many ways we are trying to explore through which this junk can either be removed or it can be converted into something useful.
Quick one, please.
Recently, we have seen this company from US doing a centrifugal launch system. What are your thoughts on that? Of the not the satellites, just the rockets as of now.
Centrifugal launch system?
Yeah, they have a huge centrifuge at the end of.
Slingshot?
Yeah, slingshot.
Yeah.
Yes, ma'am.
No, it's a good idea. There are many ways in which you can develop the required delta V. That's what you are doing. This is one of the ways. But for humans, I was thinking you are saying artificial gravity through centrifuges.
Okay, one more round of applause.